Have you ever been relaxing on the couch or away from home when suddenly you realize that you forgot to turn off the light in your room? That's not a problem anymore. If you click on this video, you have probably already seen this short. Finally, I have prepared a series of tutorials in which I will guide you step by step on how to easily create such a smart switch at home or even a more advanced one. So we will start with a basic switch controlled via Wi-Fi, but by the end you will be able to control your switch from the second half of the globe and monitor whether your light is on or off thanks to a light sensor. So in each tutorial we will add new improvements to our project until it becomes truly convenient for everyday use. Attention! In this tutorial, I will show you how to make a single light switch like this one, which lets you control only one bulb. But in the next tutorials, I promise I will show you how to make a double light switch like this, so you can control 2 or more bulbs in your room. So make sure you don't miss next tutorials by liking this video and subscribing to my channel. Let's get started. The light switch will function as so-called access point. This simply means that you will need to connect to the switch just like you would to your Wi-Fi. Once connected, you will open a dedicated web page, which I will also show you how to create, from where you can control the light. Our project consists of 2 main parts: hardware, so the physical part, and software, the invisible part, which includes the program that tells the hardware what to do, and the web interface from which we can control it. I recommend visiting my GitHub repository by typing the URL you see on the screen or by using the link in the video description. There you will find everything you need to know to do this project by yourself. What you are looking at right now is our sketch, so a plan that shows exactly how all the components should be connected to make our device work. On the left, there is a servo motor responsible for mechanically turning the light on and off. On the right, you see our microcontroller, which, as name suggests, controls the entire switch, along with a micro USB port used to upload a program from a computer to the microcontroller and to power the whole device. When you click on or off in the web page, a signal is sent to the microcontroller, which then forwards the right command via the orange cable to the servo motor, making it rotate a certain angle, by 60 degrees to turn the light on and 120 degrees to turn the light off. The brown and red cables provide power to the servo, and this power flows through the circuit thanks to the white breadboard. I will also be using a LED, but why is it useful? Well, each time a signal is sent from the web page to the device, this signal will also go to the LED, making it blink. Of course, this LED is not a necessary component, but very helpful. If something isn't working, we can check if the signal is present by simply looking at whether the light is blinking. At the end of this video, I will show you a version without the LED. However, keep in mind that if you plan to power your device using a power bank, it will not work without the LED. That's because the microcontroller and servo together don't generate enough power demand, causing a standard power bank to quickly shut off. So, to make the power bank solution work, we need to make one small adjustment in our code. The LED should stay on all the time, so it will create enough power demand, and it will only blink when a signal is received. I have already implemented this solution in the code. You can find it within comments. Of course, you can treat the power bank in a different, possibly more efficient way by making the LED blink every 2, 3 or something seconds just to test it using your own power bank. One last note, I created these sketches using the freezing application. In the future, maybe I will make a tutorial on how to use it. Currently, downloading the application costs €8, so around $10. But if you search online, you may find free installers. However, I encourage you to pay and support the developers. Before we start assembling everything to create the simple device based on our sketch, let's take a look at the components you will need. The first and most important component is the microcontroller. I chose this specific one because it's quite cheap and offers all the features we need. First, it has built-in Wi-Fi module. We will use access point mode, meaning this ESP will create a new Wi-Fi network that we can connect to, allowing us to access the web page to control the light. Second, USB UART converter. This allows us to program ESP directly via USB using the Arduino IDE. I will show you what is it and how to access it in a moment. Last but not least, it has 10 GPIO ports, which means that we can connect various peripherals to the microcontroller like LEDs, servo motors, and sensors. We will use a light sensor in the future tutorials. A small micro servo like this is power enough for our needs. The servo is responsible for physically switching the light on or off by rotating a given angle. The angles, so the right or left moves, depend on how your current light switch is configured. I chose the yellow color because it's my favorite, but there are various LEDs to choose from, so I'm sure you will find your favorite color as well. I highly recommend buying a complete set of 3 types of jumper wires. The first set is female to female. The second is male to male. And the last one is male to female. Having all 3 sets will be useful, especially if you want to experiment with different switch versions that I will demonstrate in this and future tutorials. The breadboard is used to connect all components together. However, in case of our microcontroller, one breadboard is too small, so I will use 2. You can build the project without it, and I will show you this version at the end of this video. Finally, we need a way to upload a program to our microcontroller, so we need micro USB cable for this, and we also need a way to power the device. You have several options: a power adapter like a phone charger, or power bank, or battery holder with 4 AA batteries. Don't worry, I will show you all the options so we can choose the one that's the most convenient and practical for you. If you decide to use batteries, you may also need male pin rasters and BLS connectors, because battery basket can be delivered without pre-installed connectors like this. Let's build our device following the sketch. Okay, the hardware part is ready. Now let's move on to the software. When it comes to Arduino IDE, you have two options, a web or desktop application. I prefer cloud, so the web version. It's free, just create an account and you're good to go. Let me log in and I will be right back. Okay, I'm logged in. Let's create now a new sketch. We will choose the device type later, so we can close this. Now let's return to the GitHub repository. We need one file, so I will create it, then copy the code from the repository and explain it in details. Let's rename our project. Rename. Okay. Here at the beginning is the documentation you can refer to. I think documentation is crucial in all tech-related projects because it's like a manual for building Lego. You have unlimited options, but there is only one way to build that given project. Moreover, if you are working on a project, even a simple one, always create your own documentation. This will save you a lot of frustration in the future because based on my experience, when we come back to a project after a few weeks, months, or even years, we may find that we have completely forgotten how our code works. This issue is especially relevant for people like me, whose brains prefer to remember historical facts or grammar rules rather than technical knowledge. For this reason, I will use restaurant-based related analogies to explain how the code functions. So in our analogy, the servo motor is like the cook, the server is like the waiter, the web browser is like the customer, the website is like the meal, and our request is like the order. To start, we add libraries to our program. These are pre-written sets of code that helps us perform specific tasks so that we don't have to write them by yourselves. The first library is for setting up a simple web server. So thanks to this library, the customer can place an order and the waiter can serve the ordered meal, so the right web page. The second library enables the ESP to create a Wi-Fi network that users can connect to and access that web page. The third library is for controlling the servo motor. Next, we define which microcontroller pins the servo and LED are connected to. The servo is assigned to pin D1 and the LED is assigned to pin D5. Then we set up the Wi-Fi name and password that will be created by ESP. This is similar to setting up a mobile hotspot. Remember to use a strong password. Next, we create a servo motor and web server objects. web server will operate on port 80. In our analogy, a cook is preparing meal while a waiter is taking orders. The number 80 indicates that our waiter is working at table number 80. I highly recommend tutorials on coding your own website using HTML, CSS, and JavaScript if you struggle to understand the following code. But in general, here's how it works. We store the website in the ESP memory as a constant character array named index. Doctype HTML tells the browser that this is an HTML document. The HTML document begins. The head section contains metadata and style sheets that define the page's appearance. The viewport makes the page responsive, so it means it adapts to the device screen width. This line sets the font to Lato for the whole web page if available, and if not, it falls back to a generic sans serif font. The next CSS line tells that all the text is centered. H1 header has blue color, and here we style the buttons. So the buttons text is white, background is blue, the button has 20 pixels vertical padding and 55 horizontal padding. The button text is centered. Underlying is removed from link since it's not needed here. The default border for button is set to none, so it's removed. The cursor changes to a pointer hand when hovering over the buttons. The button text is bold, and we have 50 pixels top margin to push all the content down. Then the head section ends. Next, we are opening the body section, which contains the main content of the page. The div class container, it's the main container holding all the page content. Next, we have the page header, 2 line breaks for spacing, and then we have first button on. On-click send signal on function means that clicking the button triggers the send signal function, passing on parameter to it. Class applies styling using btn class. And on is the text displayed on the button. Then we have 2 more line breaks, and the off button works the same way as the on button, but passes off to the send signal function instead of on. Our HTML page includes also JavaScript. This is where the send signal function is defined. As I've already mentioned, the send signal function is triggered when on or off button is clicked. Just like math functions have parameters, arguments, functions in programming can also have them. In this case, action is the parameter that represents the action we want to perform, on or off. Inside the function, a new object then is created, and it is assigned to the variable HTTP request. Then the open function is called on this variable to set up a GET request and define where the request should be sent. The destination is /move server ?action equals plus action, which means the request will include an action parameter with on or off value, as you can see on the right side of the screen. So if you click on, the request will go to the first address, and if you click off, it will go to the second one. Finally, the request is sent to the ESP server using the send function. Now we end body section and the whole HTML document, so our web page is also the end of our web page. Next, we need a way to display the created web page to the user. When a user enters the ESP IP address that you can see on the right side of the screen, this function is executed to show the page. This is like a waiter serving a meal. so our web page. So 200, it basically means the response success status code. The next thing specifies that the response contains HTML content, and index is our web page stored in ESP memory. I call this function blinklet because it makes the LED blink to indicate that a signal has been received. This is a simple way to provide visual feedback. When the LED blinks, we know that ESP has received a signal. The blinklet function declaration does not take any arguments and does not return any values since it is of type void. This line uses the digital write function to set the LED pin output to high, which means that the LED is on. The delay function makes the LED stay on for 100 milliseconds. Then the next line sets LED pin to low, which means that the LED is off. We can uncomment the function below when using a power bank, otherwise you can delete it, so we are going to delete it now. We don't need it. I'm going to use batteries. Here we declare the control servo function, which also does not take arguments or return any values. The function retrieves the action parameter, so on or off, from our request. This value is stored in the string variable called signal. If the user sends a request like /move servo ?action equals on, the signal will have the value on. And if signal is on, the following actions are performed. The blinklet function is called, making the LED blink to indicate the signal. Then the servo is set to starting position 90. Next, the program waits 500 milliseconds before executing the next operation. The servo moves to 120 degrees to turn the light on. And another 500 milliseconds pause allows the servo to adjust to a new position. And at the end, servo returns to 90 degrees, completing the movement cycle. However, if signal is off, the LED blinks again to indicate the signal. The servo is then set to starting position, so 90 degrees. Then program waits 500 milliseconds. The servo moves to 60 degrees, so opposite direction from before, so it turns the light off. Another 500 milliseconds pause. And at the end, servo is reset to 90 degrees, so the starting position, completing the full cycle. The last line in this function sends a response to the web browser, so the ESP moves the servo and responds with 100 OK status code to confirm the action. The setup function is called when the program starts. It is used to initialize variables, set pin modes, start libraries, etc. The setup function runs only once after each power-up or reset of the device. Here the servo motor is attached to its pin. Next, the LED pin is set as an output. This allows us to control the LED using the digital write function, which was previously used here in the blink LED function. We can uncomment the line below if you are using a power bank, otherwise we can delete it. So we can delete it because we are going to use batteries. Next, the ESP create a Wi-Fi network using the name and password that we previously set. When a user enters the ESP IP address in a browser that you can see on the right side of the screen, the web app function is triggered to serve the main web page. You can also find this IP address here in a comment. When the browser makes a request like HTTP and so on, action equals on or action equals off, the control servo function is triggered to move the servo. Again, this means that when a user clicks the on or off button, which sends request action on or off, the control servo function is executed to control the servo. The next line starts the web server on the ESP. From this point, the ESP begins listening for incoming requests. And the loop function does exactly what its name suggests. It loops all the time, allowing the program to react and respond to different events. It is similar to a waiter in a restaurant, always listening for new orders for our requests. So now our program is ready. Let's upload it to the device. Plug the microcontroller into your computer via USB. Select the correct device. But before, make sure you have Arduino Cloud agent installed. It is a required plugin that enables serial communication between your board and the Arduino Cloud, accessed via your web browser. You can find the link also in my GitHub repository. Start typing node and choose 1.0 since 3.0 is not listed. Now we can verify the code to ensure there are no errors. Next, upload the code. If the upload fails, the issue may be an old micro USB cable. Even if the cable looks fine, it could be damaged internally. I had this issue before, so I bought a completely new cable and it solved all of my problems. Okay, the program is uploading. You will see a blue light blinking, indicating that the program is being uploaded to the microcontroller, like here. Okay, the program has been uploaded. One last thing, if you get a port busy error, you can open a device manager, find ports, locate your device, and disable and enable the driver. This usually solves the issue. It's time to test our device. The boards are covered with double-sided tapes, so I'm using them and a drop of superglue to place the servo. Now power on the switch, find your ESP Wi-Fi, enter the password you set, and visit the web page to test it. As I promised, I will show you 3 different power options, a version without a LED and a version without a breadboard. The first option is using a USB charger, which can easily be swapped for a power bank. However, remember that this requires a small code adjustment to generate enough power demand. You will find a ready solution commented out in the code. If you are using a battery basket, it can be delivered without pre-installed connectors. In that case, you can use male pin rasters and BLS connectors to create a custom connector yourself. This project can work without a LED, as I explained earlier in this tutorial. If you decide to remove the LED, I advise you to update the code by simply deleting the parts that control LED. We can also build the project without a breadboard by connecting all components directly to the microcontroller. I will show you how to do this now. you for watching my very first YouTube tutorial. I hope it will be useful for you and that you will enjoy it and dive deeper into the fascinating world of technology with me. Through my channel, I want to show that even if you are more into languages or arts rather than into IT, just like me, you can still explore and understand technology. I think I was the last person in my class to have a smartphone, really, and it was not about finances. Also, feel free to share your experience in the comments below, and if you post a video of how it works in your home on social media, don't forget to tag me. I would love to see your results and leave a comment. See you in the next tutorial, where we will develop this project by adding a second servo motor to control 2 and more bulbs in your room.